All right, so started the recording. So before the break, we check our accuracy with regards to the sum of squared error. That is okay. I think this is one of the most what I call it chosen approach. And the other one is that you can also what I call it determine the accuracy by plotting so-called a scatter plot between the data and also the predicted values. For example, here, as I said just now, we could also say that this set of values here coming from our data, because this is coming from, for example, here, it's coming from the delta CA over delta T. And the model is predicting that the value is supposed to be 0.162, whereas the actual data is 0.16, and so on. So you can see there is some small discrepancy, especially when you can see here, small discrepancy between the data and the predicted values. So how can you determine the accuracy visually? So you can just select these two values here. Maybe we can get the two values from the top, and then go to insert and choose the scatter plot. And then from here we can see that we have the x-axis referring to the experimental data values, and the y-axis here referring to the predicted values. So the idea here is that you want to get a straight line passing through the origin in such a way that all the points here, all the data points here, fall along that line. So we could add one trend line. And then this trend line here is that we want to set the intercept equals to 0, because we want the line to be passing through the origin. And then we want to display the equation on the chart as well as the R-squared values. So you can see that, okay, let me enlarge the values here. You can see that the accuracy is quite good, because the R-square is a number which is very, very close to 1. And then you have got an equation. Initially, ideally, you will want to get y equals to x, because these two values are supposed to be the same. The data and also the predicted values. So the first one, okay. The second one, a bit underestimation. Third one, okay. This is underestimation. This is above estimation. So basically, the R-square value is just an average, between the over and also the underestimation. Okay. So we could also check the second approach. So I'm just going to use the same plot by changing the values here coming from my blue table. Hit OK. So I can see that there's some underestimation and also above overestimation, but essentially my R-squared value is also quite good, which is a number close to 1. And then y equals to x, which is quite okay also, because 0.9967 is almost 1. So the second approach is also okay. It's also accurate in a sense. What about my third solution here, my third approach here? Okay, repeat the same procedure. Select the new data range. These are the new data ranges. Okay, and hit OK and check on the values here. It's also not too bad. So visually, you can see that, okay, this is much better as compared to the rest of them, because the rest of them you have got some over and also underestimation. But from here, you have got less, over and under. In fact, there are only 1, 2, 3 points which do not fall along this linear line. However, this is not the end of it. This is not a good tool to see that we have got an accurate prediction. The one that we want to check is definitely this one here, whether these are close or far away from the values that we expected. So the values here, I would say that we have the most confident with, because once we linearize the nonlinear equation and then finding the slope and what do you call it, the y-intercept, and from there we calculate the m and k, provided that we do not have any runoff errors, then I would have more confidence with these values here rather than these values here. Although SSC here is a very, very small number. And then just now you can see the scatter plot, and the plot between these two will give you a very good correlation. Yeah. So let me do that again. Add the trend lines, set intercept to 0, and then display the equations. Okay. Right. So here is quite good. This is y equals to x, and then r square equals to almost 1. Right. So we have discussed about topic 2 basically, but I would like to go over topic 3 right now with the groups. So we close topic 2 and we start with topic 3, question 4, right? Okay, question 3 was done. You just give me 1 second here. By any chance, group 7, have you forwarded your solution to me? Can I check group 7? Oh yeah, Kayong, you have forwarded the solution in the Excel format, eh? All right, so Kayong, would you like to go over the solution?
Yes, okay.
Yes, go ahead, Kayong.
Yeah,
Okay, just give me 1 second. Okay. Maybe we can go over the problem first, eh? All right. So we have got a reaction to A1, a reversible reaction here. A2 and A3 are your products. With K1 and K2 are the rate constants. K1 is the forward and K2 is the backward rate constant. And you want to carry out this reaction in cascade of stirred tank reactors. So maybe there are more than one, yeah? And you are given the flow rate, and this flow rate refers to the volumetric flow rate because the unit is cubic meter per hour. And you have got the feed concentrations of A1, A2, A3, yeah, with the corresponding values here. And you are given the rate constant for the forward is 10 meter cube per kilomole per hour. So just remember that if you're given a rate constant with the following units, then definitely this is a second order reaction. Okay? I've shown you how to determine the second order rate constant units. So make sure that you refer back to the discussion, our previous discussion. And then Kc was also given as 16.0. And then you want to obtain 80% conversion. Okay, so first, what is the size of the vessel? If only one vessel is to be used. So this is one of the first step of the analysis done in this kind of problem. Okay, you want to carry out the reaction in multiple CSTRs, but then you want to check whether if I were to run the experiment using just one vessel, what would be the volume of the vessel? Okay, and then part B, if I want to use smaller size CSTRs rather than one big one, which is in part A, but the smaller size means this is just 1/10 of the size of the one CSTR. So this is 1/10 of the size of the big CSTR. Okay, so find the number of the CSTR that is needed in order to achieve the same conversion. What is the conversion? 80%. Okay, so once you have done that, you repeat the whole thing with a graphical solution. Okay, so you could do so because you know CSTR is probably the easiest one to calculate the area under the curve. Yeah, provided you know what kind of curve that we're talking about here, or what kind of graph that we are plotting. Okay, so Kayung, the floor is yours. Go ahead and then discuss about the solution. I got you here. Where do you want to go?
okay. So this is the condition of the experiment.
Mm-hmm.
Initial concentration and flow rate and K1 here.
Mm-hmm.
And
Okay.
okay, but first we need to find out the equilibrium conversion. So
Okay.
since that it tells us that the initial concentration of A2 and A3 is 0, so that the rate of reaction is the equation of the rate of reaction is like the row 7.
Okay, this one.
Yeah.
Mhm. Okay,
So
can you proceed?
yeah,
Yeah.
when equilibrium, we can find out that the XE, the conversion equilibrium,
Okay, these values.
and the values is 0.889.
And this is obtained from, okay, one thing that I can suggest to you, Kayong, or the other students, that can you try not to put in numbers here unless it is really necessary. So what you put in the formula, normally we put in the cell number, because after that, you could manipulate the numbers from the cell. Otherwise, you have to go to the formula and then, change the values from the formula, which is not something that is efficient. Okay, right.
Okay.
Okay, please
Yes.
proceed.
Okay.
Mhm.
So since that the reaction is using the 80% of the equilibrium conversion,
Okay,
so yeah, so
so
we
this is
get the
80% of it.
yeah.
Okay, so this is
And
okay. Mhm.
yeah, so and then we can find out the tau
Okay, where
with
is it?
the formula. Yes, here.
From here. Okay,
Yeah,
how do you find the tau?
yeah, found the tau. Then we can find out the volume.
Okay, how do you find the tau?
Yeah, the formula is at the row 14. Row 14.
Row 14. Oh, okay, this is the design equation.
Yeah,
Okay.
we just sub in the information, then we can find out the tau.
I remember the question that I asked earlier. The design equation consists of what variables, or how do relate the variables? This is tau over CA naught
Yeah.
equals to XAF minus XAI. These are conversion over minus RA. So this is the rate of reaction. So remember that tau is nothing but V over V prime, right? So we can have the rate also in the design equation. Okay, please proceed.
Yeah. So the question A is done.
Okay, so you've got the volume of one single large reactor, which is 62.7.
Yeah.
All right, good. And then part B.
Part B is the question is talks about the how many tanks to achieve the same conversion
Mm-hmm.
if the volume is changed.
Mm-hmm.
So the new tau is 0.062.
How do you get this? This is
Yeah, because he says that the is 1/10 of the size calculated in A, the volume.
so 110 is this multiplied by zero point 0.1
0.
divided by 100.
Yeah, the 100 is the flow rate.
Oh, the flow rate. Okay, all right. Okay, so this is 110. 0.1 is 1 over
Yeah,
10. And then you divide that by the 100 is the flow rate, or is the
the
flow rate?
flow rate, flow rate.
Okay, so this is basically V divided by V prime, which is
Yeah,
your term. Okay, good.
yeah. So this is the new tau.
All right.
And then we can find using the new tau, and we sub
Mm-hmm.
in the formula, and we
Mm-hmm.
can find out that the XAI. So we need to find the XAI instead of the XAF because we need to do a reverse calculation.
Reverse calculation. So
Yeah, to
you're
find.
going to start from the last CSTR.
Yeah, yeah.
Okay.
So we do the calculation until the XAI is equal to 0.
Mm-hmm.
Yeah, so we, and then we can say that it needs 4 tanks to achieve
So
the
it
same
is 4 times.
conversion.
So
Yeah,
you have
one,
got
two,
five conversions. Five
yeah,
conversions means you just need 4 tanks.
yeah,
Okay. Let me check. How do you get 0.711? This is coming from D12. This is from 80%. So basically, this is the final conversion that you want to achieve,
yeah.
0.711. And then how do you get this value here?
Uh,
Uh, can
yeah, using
you, uh,
formula
Can you explain a
at
bit?
row 21.
Row
The formula.
21. Okay.
Yeah,
So
we
this
find
formula
out
here.
the XAI. The XAI is the XA4.
Okay. So
Yeah,
basically you are solving it backward. You start with the last tank and then you want to find the XA n minus 1 basically.
yeah.
Yeah. So assuming that your last tank is the n tank and you want to find the one which is before that.
Mm.
Okay. Right. And then you want to ensure that the initial conversion is 0, and this is corresponding to the inlet stream here.
Yeah.
Okay, the conversion at the inlet stream. Okay, all right, acceptable. So can you guys follow Kayung's solution here? Can just double check the chat box here whether you can follow Kayung's solution. Anyone? Yes, Amisha say yes. Or what the rest of you? Hanis also say yes. Please let me know if you cannot follow the solution because Kayon's solution is given in the Excel form and there's a lot of formula there. Okay, good. So I can get we can move on basically to the next part here. All right, so assuming that part B, you know it, yeah, let me just repeat it. XA5 here is the conversion, the final conversion, XAF basically. And then before that, you have got one tank. So if I were to draw, yeah, this is just a very quick drawing here. And then copy the tank, right? And put in arrows here to represent the feed stream. The arrow here is not straight. Okay, and then maybe 1.5. Okay, and then copy down the arrow. Okay, I'm just going to quickly, draw something so that you can visualize what happens here. Not one. All right, and also maybe we can put in the Y arrow and text box. Okay, so this is what Kayong called XA5. Okay, so XA5 is your final value here, which was obtained as 0.711. Correct, Kayong?
Yeah.
Okay,
Correct.
and then here is XA4. And the first one is what he called it XA1. This is XA2, and this is XA3. Okay, so what Kayong did, if I can just re-explain what he did just now. Initially, he calculated the tau value, which is from one big CSCR. Okay, let's say this is one big CSCR. He can find the tau value, and then from there he can determine the volume. And then we say that we want to maintain the flow rate, which is 100, whatever the unit. I forgot the unit. So we fix the flow rate. So the flow rate will remain fixed here. What is changed? The volume of the CSTRs. Okay, now the volume has been shrunk to about 1/10 of the original volume. So 1/10 of this is 1/10 of 62.7. So it's a 6.27, right? And then if you divide that by the flow rate, then you're going to get the new tau. So each one here, tau 1, 2, tau 3, and tau 4 has the new tau value here. And they are the same. This is because basically we want to maintain the size of the CSTR in series. And Kayong worked backward. So initially he got XA5. how he got it from the design equation. So we said that we want to have the final what do you call it conversion, 80% of the equilibrium conversion. So he did it here. So you just take 80% of this XE value. The value here is 0.711. So basically XFI is 0.711. And then using the design equation for the final CSTR, he can back calculate to get XA4. How? Well, because design equation is saying that tau over CA naught, which is here, equals to XA5 minus XA4 divided by minus R. Yeah. So minus R, he got it from somewhere here. You just need to find the rate equation from the here. Here's your minus R value. Yeah. This is the equation for it. Okay. So once you plug in the equation containing CA naught and then X, not XE per se, in here is the whatever the X values that you are interested in. Okay. And then you put in the appropriate values so you can back calculate to get XA4. And this is what he did here. Okay. So he got XA4 from putting in the appropriate values in the rate equations. And then once he got XA4, then he can back calculate to obtain XA3 and then back calculate to obtain XA2. And then lastly, obtaining XA1, we want to ensure that XA1 here, since there's no conversion, XA1 here equals to 0. Yeah, so you are doing basically iterative calculations in order to determine that XA1 equal to 0 and then you stop. And then from here, you can just count. This is tank 1, tank 2, tank 3, and tank 4. So we just need 4 tanks in series. Correct, Kayung?
Yeah. Correct.
Okay, right. So the graphical solution, part C?
Part C is we need to plot the graph. It's 1 over the rate of reaction.
Okay, here.
Against the X, the conversion.
Against conversion, okay.
Yeah. So we need to calculate the 1 over rate of reaction first. Then we plot in, and then the XA is using the same previous in the question B there.
Okay. Right. So this is 1 over this one. Okay.
Yeah, is the rate of reaction.
Okay. So basically, once you have got 1 over minus RA as well y-axis and then the appropriate conversion for it, we can basically determine the area, this rectangular area, basically, right, Kayong?
Yeah, under the curve.
Okay, so if you use a PFR, then it's going to be area under the curve. But if you use a CSTR, basically, this is the area that you're interested in. Correct, Kayong?
Correct.
So Kayong has done it over here. Let me just go back. So basically, Kayong, if I can carry on with the discussion, the horizontal value here, which is the length of this rectangle, is 0.711. What does it mean? It means that this is the final point here. It's 0.711, which is your XA, the final XA value. And once you find the corresponding 1 over minus RA value, then you're going to get 0.588, which is the Y value here. Yeah, so you have got the height, which is 0.588, and you got the length, which is 0.711. If you multiply these two numbers, you're going to get the area of this rectangle. So what this area represent, Kayong?
The volume.
The volume.
No, the top, how to say?
The tau, right? The tau over CA naught.
Yeah. Tau, yes.
So coming back to the design equation, basically, it is the tau over CA naught, which is equals to XAF minus XAI. This one. So tau over CA naught equals to XAF minus XAI divided by minus RA, right? So basically, this the second part here, which is the right hand side of the equation, is nothing but the area of this rectangle. And once you calculate the area, that value is tau over CA naught. And then you can calculate the tau, correct? So the tau is nothing but this multiplied by this multiplied by B2, CA naught. Okay, CA naught is B2. And then you multiply that by XA5 and then here. All right, it's because you have got from the design equation here, tau over CA naught, then it's going to be XAF, because XAI is 0, so denominator here is basically 0.711. Multiply that by 1 over minus RA, which is 0.588, and then multiply that by CA naught, which is 1.5. And that's why you got the value to be 0.627. Okay. And then the volume, you just need to multiply that by the volumetric flow rate, which is here, 100. Please don't forget to put in the units. I would like to strongly encourage you to start practicing putting in the units. You have put in the units in some cells here, but then here also, if you can, just put in the units, especially when you want to submit this Excel file in the exam later on. Okay.
Okay.
Right. I think that's good, Kayong. Okay. So how do you determine the number of CSTR that you need?
Yeah. Can you repeat?
The question is asking you not only to determine the volume, but also how many CSTR that you want to use from the graphical method. So now you have got the part of the solution. Yeah, you have got one big value of the what I call it CSTR here, but how many multiple CSTR that you want to use for this kind of reaction?
We need to also need to file that how many tanks based on the graph.
Correct, because if you see part C here, repeat the calculations of part A, which you did just now, okay? And then B here. So B means that how many CSTR that you need in order for you to get the same conversion, which is 80% of the equilibrium conversion graphically. Okay, so how do you do it?
Using the actually, no, I have no idea.
Okay.
Yeah.
Right. That's okay. So can I give you an idea? Okay, let me copy this rectangle here. So I want to start with here. What is the value here that I'm interested in? Did you remember the problem statement here?
Yeah, a tank, the volume of the one tank, right?
Yep. So this is 1/10 of the volume of the big tank. Correct?
Correct.
Okay. So basically, this is my big tank. Yeah. This is tau over CA naught for my big tank. This is tau over CA naught for my small tank. And I may have multiple of them. With different sizes. This one could be like that because depending on my conversion. So you have got your conversion here. How did you calculate this conversion here from graphical method? Okay, you just plug in from here. Okay. Yeah. So you can see that you have got basically the X values here. Yeah, the X values. Okay. So let's start assembling all these rectangles here. The first one, you start from 0.711, which is your final conversion. And then you go to the second one, which is 0.64. 0.64 is somewhere here, correct? So that is my first rectangle for the small CSTR. Can you guys follow our discussion? Yes? Up to the first small rectangle, can you follow the step? Yes, all right. And the second one, you start with the same conversion, and then you go to 0.52. So 0.52 is here. Okay. So can you see that this one is a bit, thicker compared to this one? Okay, let me change the color here. Maybe using a different color just to distinguish between the two. So it doesn't make sense, right? Because this one, the width is larger than the width here, although they share the same height. If I want to keep the same volume, I would have to reduce the height yeah, so that the tau over CA naught value for the two here will be the same. Correct? Basically, the area of the rectangle here, I want to maintain to be the same. Okay, so the next one, let me change the value here. So the color to be probably green. Okay, I want to start with same thing, which is 0.52 all the way to 0.31, somewhere here. So this is even thicker than the previous one. So I would expect that the height would be even lower. How much lower? Okay, then we talk about that, how much lower later on. Okay, and then what about the last one here? The last one here, we want to go to 0, and then we extend it all the way to here. This is even thicker than the rest of them, right? So the width here is the largest, this is second largest, and this is the third largest, and this is the smallest. Right. So what you have learned so far, you have learned that once you put in the rectangle here, the first one is that you want to choose the final value of your conversion, which is this point here. And this will correspond to the corner here. All right? Like that. And second one here, you also want to do the same. You want to go down so that you reach the line here. The corner here must be crossing that line, that curve. Isn't it? Does it make sense?
Yeah.
Right? Because you have determined the conversion. So essentially what you are doing is that you have got the conversion, the intermediate conversion of 0.64. You go up, and then once you cross the curve there, and then you go to the left. And then you stop somewhere when you reach the second, the next conversion, which is 0.52 here, right? And then you repeat the same step. Over here, you want to reduce it down to the next, what I call it, corner, so that the corner will be touching the line. Yeah. And then you want to ensure that this is the next conversion, which is 0.31. And the last one here, do the same thing because this is much thicker. The width is the largest. Then you know that you have to go down all the way. And this will be the height, the new height of the final rectangle. And from the calculation later on, you will ensure that this volume, which is representing by tau over CA naught value, and this one, that one, and also the last one, they must be equal. Because we specify that we want to have 1/10 of the large reactor size. Yeah. Okay. So if I were to go into the solution here, this is what happened. So the first one, you start from 0.711, and then from there you have got one rectangle here. This is the thinness of the 4 rectangles, and then after that you go with the second one. Same thing as what I did just now. So you can see the corner here must be touching the curve. And then the other one is same thing. The corner must be touching the curve, and here the corner must be touching the curve. Okay. And then you find the corresponding value on the y-axis so that you can find the new area for all this thing. Okay. And once you have done that, you will notice that the final, what do you call it, the final solution will be similar to the one that you did numerically from the second part of it, from part B. So we just need about 4 tanks. Okay, right. So having said that, I think it is not what do you call it, efficient if we go over question 5 very quickly because we are about 10 minutes before 1. I know that Group 8 wanted to present their solution, but can I suggest that we stop here and then give it a thought? I want you guys to go back and then redo question 4, and as well as the Excel problem from topic 2, yeah, so that you can really understand how to solve non-linear equation, how to solve for some parameters in the non-linear equation using the Excel solver. And then tomorrow is a public holiday. I don't want to rush things because we still have plenty of time, basically. I want you guys to really understand all the concepts and steps before we move on. Yeah? If we rush everything, then some of you may not be able to catch up. So please go back and then try to solve Q5, even though Group 8 has provided the solution here. I think here is probably better if we postpone the discussion to next week, next Wednesday, rather than rushing through within 10 minutes. Okay, so we stop here. I know that initially I wanted to wrap up topic 3, but it's better not to do so today. Yeah, rather than rushing down, I think it's better to postpone the discussion on the remaining question to next week. Right, so we stop now. Thanks very much for listening to me, and I hope the rest of you who missed our session this morning could go back and watch the video. Yeah, and please remind your friends, if you know your friends who missed our session today, to watch the video, especially on the using Excel solver just now. Okay, so let me stop the sharing of the screen and then stop the recording as well. And then we have